Hi, my name is Ty Williams, and today we're going to be describing microbial death. This is a graph of your typical microbial growth phases. You start with the lag phase, which is where the cells are adapting to their environment. You go to the exponential phase, which is where the cells start to grow and multiply, and then you reach the stationary phase, which is where there is no overall increase in numbers. And finally, you reach the death phase, which is what we're going to be discussing today. This is a graph expressing the relationship between N, the number of microbes, and time. As you can see, as your time increases, the number of microbes die exponentially. If we wanted to graph the death of microbes linearly, we could do so using log. Now, if you get to the equation portion of this here, you got your K. You calculate your K, which is your proportional constant, using the natural log of the initial number of microbes minus the natural log of the final number of microbes over the final time minus the initial time. You can then use this K to calculate your D value. Your D value is going to be 2.303 over your calculated K. If you wanted to find out the N number of microbes that you are going to end with, you can use this formula here, which is the initial number of microbes times E, and your negative K times time. So if you were given a certain amount of time, you could figure out how many microbes you were going to be left with at the end. Now, the relationship with this graph here is showing you that if you were to go to a 1 log reduction from 10 to the negative 4 to 10 to the negative 3, for an example, the amount of time it took you to achieve that 1 log reduction is your D value. So to illustrate what a D value is and its importance, we can talk about something that everybody likes to do, and that's bake. So we can bake some muffins, and at this particular second, you have 10 bacteria in this muffin. If you were to put this muffin in an oven for 175 degrees Celsius for 3 minutes, which is going to be the equivalent of your D value for this muffin, you would achieve a 1 log reduction, and 90% of the bacteria has died, and you're left with this single bacteria here.
Hi, my name's Chris. I'm going to be explaining Z values. So we just talked about D values, and obviously your D values are not static. They're going to change with temperature, and this is how you can visualize how your D value is going to change with temperature. It's going to exponentially decrease because it's pretty intuitive. As your temperature increases, it's obviously going to take less time to kill any microorganisms there. Now, similarly, like we did before with bacterial numbers, we can take that graph and make it linear by graphing the log of D over the temperature. So let's say we have 10 to the 2 D value, 100 minutes, and we went to 10 minutes using a different temperature. That difference, that 1 log reduction in D, that difference in temperature is going to be your Z value. Your Z value is what you're using to achieve a 1 log reduction in D values. Now, using equations, we can get our Z value by taking the final temperature minus the initial over the log of that initial D minus the log of that final D, and we get our Z. If you want to find a D value, a final D value, you can use this equation. If you have a Z value to calculate your final D, this equation is just derived from this equation. Now, how this would look in the real world. Let's say we have milk. Milk is obviously always pasteurized before being sold in a store. Listeria monocytogenes is a pretty dangerous organism that we definitely want to kill in milk using heat, by heating up the milk and pasteurizing it. The D value at 60 degrees Celsius specifically is 8.3 minutes for Listeria, and its Z value is 5 degrees Celsius. So let's say we heat up our milk, commercial example, we heat up our milk 60 degrees Celsius for 8.3 minutes. We've now achieved a 1 log reduction. We've killed 90% of those bacteria. That's usually not good enough in industry. You want to kill many logs of bacteria. Generally 9D is something that they'll do. So if you want to achieve a 9 log reduction, you simply multiply your first D value, 8.3, by 9. You get 74.7 minutes. We've now killed 9 logs of Listeria cells. Now, using our Z value, we can manipulate this a little bit. if we go from 60 degrees Celsius to 65 and add that 5 degrees Celsius, we've now achieved the 1 log reduction in D. So our D went from 8.3 to 0.83, 10% of that. So now it's only going to take 0.83 minutes to achieve a 1 log reduction. Now I can simply multiply that by 9 to get our 9 log reduction, and it's only going to take 7.47 minutes now at 65. So as you can see, we went from over an hour to achieve a 9 log reduction to only under 10 minutes by only increasing the temperature by 1 Z, by 5 degrees Celsius. And that's how they'll do it.